In recent lectures where I focused on linear algebra content for our course here, I focused on the idea of diagonalization of square matrices based on eigenvalues and ideally linearly independent eigenvectors that form a basis for Rn. Here in lecture 28b, that continues. First, let's address why does diagonalization work in the first place. I'm not going to give a full proof of it, but I'll write a couple equations that should make it more believable in the general case. Then I'll look at the topic of complex diagonalization, where I allow for my change of coordinates matrix to have complex number entries, and my diagonal matrix, for that matter, to have complex number entries. We won't apply that content, but it's good to do it to round out the picture of what can go on. More importantly, we'll go on to real canonical or normal forms for matrices with complex eigenvalues based on real changes of variables and the implications for systems of linear ordinary differential equations. So again, why does diagonalization work? That's the first thing we want to address here in lecture 28b. When A has eigenvectors that form a basis for Rn in general, for when A is an n by n matrix. So here is the statement of the diagonalization theorem again. An n by n matrix A is diagonalizable over the real numbers, is how we've talked about it so far. So the change of coordinates matrix P has real entries, and the diagonal matrix D has real entries. If A has n linearly independent real eigenvectors, that will definitely happen if you've got n distinct eigenvalues, which would all necessarily have to have multiplicity 1 in that case. In other words, A is diagonalizable if it has a list of eigenvectors that form a basis of Rn called an eigenvector basis. Furthermore, we can say that A equals P D P inverse, where P has columns. The columns of P are the n linearly independent eigenvectors of A that we found. D is a diagonal matrix, and in fact the entries on the main diagonal of D are exactly the eigenvalues of A that correspond in the same order to the eigenvectors in the columns of P. So if the first column of P is V1, and that's an eigenvector for the eigenvalue lambda 1, lambda 1 needs to go in the upper left corner in the first column of D. The key reasons for the truth of this theorem are, first of all, the definitions of matrix multiplication, which is what I'm going to really focus on. Also the definition of eigenvalues and eigenvectors, which we have focused on, but will come into play again. And if you want a fuller proof, you also need the invertible matrix theorem. Here are the key equations that help you believe that this is true. Rewrite this equation that we'd like to verify. A equals P D P inverse in the form, after right multiplication by P, AP equals PD. Which we also could solve for D after left multiplication by P inverse, but I'm not going to bother. I'd like to see why those two expressions are equal. Here it goes back to the definition of matrix multiplication that we talked about. Square matrix A, n by n, times another square matrix P, n by n. If we write the columns of P as V1 through Vn, which are going to be eigenvectors of A, corresponding to the eigenvalues lambda 1 through lambda n. Remember, way back when, I don't remember what lecture it was, I said you can define this product to be this matrix here, where you've got still n columns, and the columns are AV1, AV2 through AVn. That was the definition of the product of two matrices. You can figure out these things by doing the definition of the product of a matrix times a column vector as a linear combination of the columns of the matrix with the entries of the vector as the corresponding weights. I don't need to bother with that here because each V is an eigenvector for the corresponding eigenvalue, and I see there's a typo here. I can write it this way, where this is lambda 1, this is lambda 2 through lambda n. Okay, so evidently, if I'm going to verify this, P times D must be the same thing. And it is. P times D, here's P, here's the diagonal matrix D with the eigenvalues along the main diagonal. And once again, I continued my typo here. This should be lambda 1, lambda 2 through lambda n there as the scalar multiples. Here it seems I'm just sort of jumping to the end. Am I really using the definition of matrix multiplication here? Yeah, I am. Without explicitly showing it. For example, take this column, and what goes in the first column of the product? It would be this entire matrix P times that first column. But that would be a linear combination of V1 through Vn with these numbers as the weights, and only the very first one is non-zero. So we get lambda 1 times V1, which is what you see there. For the second entry, right there, second column I should say, take the second column of this matrix, take P times it. Once again, take a linear combination of the columns of P with these numbers in this column as the weights. The only one that's non-zero is lambda 2 times V2, giving us this, etc. And these two matrices are the same, okay? So that helps you believe this equality here, which would help you believe this equality as long as P is invertible. But we know by the invertible matrix theorem that P, this matrix right there, will be invertible if and only if its columns are linearly independent, which is what I'm assuming in the diagonalization theorem. Okay? So that should help you believe it without being a full proof. All right. But what about if the eigenvalues and eigenvectors are complex numbers? We have encountered that before already. In terms of solving differential equations, we wrote out our complex solution, used Euler's identity to expand it in terms of a real and imaginary part, and then we took those real and imaginary parts and made them part of a real solution that's a linear combination of those, and those are both real quantities. But can we diagonalize it? Not with real matrices P and D. However, if we allow complex entries for P and D, then we can. Because the algebra is the same. In that previous slide, that last thing at the bottom that I did, that algebra would still work even if the lambdas were complex numbers and even if the vectors V were complex vectors. There's nothing stopping us if we allow for complex diagonalizability, allowing matrices with complex number entries. Here's an example from lecture 23b. We're going to consider this example in a couple spots here. Take this matrix A, find its eigenvalues. We found them to be -1 plus or minus 2i before. You might want to check that with the, figure out the characteristic polynomial and then use the quadratic formula. And it also turns out the corresponding eigenvectors are these. So lambda 1 is -1 plus 2i, and lambda 2 is -1 minus 2i. V1 is I1, V2 is -I1. Oops. Let P be a matrix with complex number entries whose columns are these two vectors, plus I1 and -I1. That's what I did. It's analogous to how we diagonalized real matrices with real, we diagonalized matrices with real number eigenvalues based on eigenvectors in P that are real eigenvectors. The algebra should still work. P inverse will be 1 over the determinant of P. The determinant being I plus I is 2i. Once again, do the usual thing, swap the numbers on the main diagonal. The I and the 1 get swapped like that. And negate the numbers on the off diagonal. The negative I becomes positive I, the positive 1 becomes a -1. Dividing by I is the same as multiplying by negative I. I talked about that recently. So dividing by 2i is the same as multiplying by -1/2 I. -1/2 I times 1 is -1/2 I, negative I over 2. Negative I over 2 times I is positive 1/2. Because I times negative I is positive 1. Negative I over 2 times -1 is positive I over 2, and negative I over 2 times I is positive 1/2. Same as we got with this one. That's the inverse matrix. Go ahead and take the time to check that P times P inverse is the identity matrix. It does work. So then, what happens when we compute P inverse AP? Do we get a diagonal matrix? Yes. You can check all these calculations. Here's P inverse times A times P. Go ahead and do these calculations. Check it. You get a diagonal matrix with complex numbers that are non-real along the main diagonal. So it can be done if you allow for P and D to have complex number entries that are also non-real. We're not going to see any applications of this though. Okay? So let's move on. Don't we really want P and D to be matrices with real number entries? Don't we really want that? P at least, so that the change of variables, the change of coordinates is real? I mean, maybe we can't avoid D to have complex numbers, or maybe we shouldn't shoot for a diagonal matrix. That's similar to what we did with Jordan canonical form. We didn't shoot for a diagonal matrix there, we shot for an upper triangular matrix with a 1 in the upper right spot. Similar kind of thing here with complex eigenvalues. We're not going to try to diagonalize it, but we're going to try to get it into its canonical form, normal form, best form. We can sacrifice diagonalizability, but is there a consolation prize? The answer is yes. We can still convert a general real matrix A with complex eigenvalues to a form that is nice. The downside is it won't be diagonal. So it is a little harder case to consider, as, for example, in figuring out the matrix exponential is hard. Our example from 23b is actually already in the nice form. What was the example again? I believe it was -2, -1, 1, -2. I think it was that. I mean, I better just double check that. -1, -2, 1, -2, yes. Oh, no, sorry. Wrong. Looking right here. -1, -2, +2, -1. This is already in as nice a form as it can be, actually. But there's a pattern, and we're really after that pattern. Here's the pattern. We're after matrices that look like this, which are not diagonal, but still have a nice pattern to it, I guess you could say. A negative B in the first row, B negative B A in the second row. Or if you prefer, you could switch the signs on the B's because this is just emphasizing that they're opposite signs. That numbers on the off diagonal have opposite signs. So it doesn't matter whether I really write it this way or I write it this way. This way is going to be a little bit more convenient, you might say, especially when we ultimately relate them to rotation matrices that I'm going to hint at here in this lecture, but won't talk about more fully until lecture 29b. All right, let's do an example. This is the main example for the rest of this lecture. This is a real matrix with complex eigenvalues that's not in this nicer form from the previous slide, the C, with the A and the B. Here's our example. So it's not at all obvious that this has complex number eigenvalues, but if you calculate the characteristic polynomial, set it equal to 0, use the quadratic formula, you get -1 plus or minus 2i, which has the same eigenvalues as this one. That's good. Same eigenvalues. They are going to be similar matrices. It turns out from the change of coordinates. What we've usually done with this at this point, when we've talked about differential equations at least, is we've usually just taken the negative of the something plus something times I. It's going to turn out to be more convenient here to take the something, in other words, the real part, -1, minus the imaginary part times I, the second eigenvalue. That's going to be a little bit more convenient. I could do it with the first one, but it's going to be a bit more convenient to do it with the second one. Let's find the corresponding eigenvector. As usual, this is a homogeneous system corresponding to the equation a minus lambda I times v equals the 0 vector, and I'm trying to solve for v. A non-trivial solution is what I'm after. It's not at all obvious, but these two rows are multiples of each other. They are. You can check it out. You can take 4 divided by 6 plus 2i and check that it equals negative 6 plus 2i divided by negative 10. It does. Check it. I checked it before the lecture here. Divide the number in the bottom row by the corresponding number in the top row, and it works out. And also a reminder, to get from here to here, you need to subtract negative 1 minus 2i, this lambda, from upper left entry and lower right entry. 5 minus this is 5 plus 1 minus 2i, excuse me, plus 2i, is 6 plus 2i. And negative 7 minus this is negative 7 plus 1 plus 2i. That's negative 6 plus 2i. You do get a row of zeros. We can just look at the first equation. In terms of solving for I, x as a function of y. And this is like saying 6 plus 2i times x minus 10y equals 0. This first line here. I'm not bothering to go to reduced row echelon form. Add 10y to both sides, divide both sides by 6 plus 2i. I can write this. I can also divide the top and the bottom by 2. And then it's simplest, if you want to get rid of fractions, to not let y, your free variable, equal 1, but instead let it equal 3 plus I, so it cancels with that 3 plus I. So this vector, where y is 3 plus I and x is 5, is an eigenvector, a complex eigenvector for this complex non-real eigenvalue. It will be good to split it into its real part plus I times its imaginary part, because based on some things we were inspired by before, we've had success with real and imaginary parts as relevant for our real problems before. Maybe we'll have success again? Yes. Take those real vectors, 5, 3, and 0, 1, and put them in a P matrix as columns, and that P matrix will work to convert this, not to diagonal, but to the nice form. Let's check the details. So notice the columns. 5, 3, and 0, 1 are the real and the imaginary part of that complex eigenvector. This matrix is invertible. Its determinant, 5, is non-zero. Its inverse is this, 1/5 times, swap the numbers on the main diagonal, negate the numbers on the off diagonal, distribute the 1/5 to the entries of the matrix, and then check P inverse times AP. You can go ahead and check all these calculations. Does equal that thing, our C matrix. It does equal the same thing we got with our other example that was already in the nice form. Go ahead and take the time to check it. It really does work. Okay? Why does it work? I haven't explained it. The verification I did here at the beginning of 28b would not work, because we don't get a diagonal matrix, for one thing. It can't work. There's got to be some other verification to know that we're going to get the matrix to be in that form, that canonical or normal form. A, negative B, B, A, where in this case A is negative 1 and B is 2. To make those match. It's the same matrix again as the original example. Here's our last slide. Then we'll look at Mathematica a bit. I think this is the last slide. How is this related to differential equations? Let's go ahead and consider a differential equation, a linear system, with this matrix that we've just been working with, that has eigenvalues negative 1 plus or minus 2i. We can certainly try to draw the phase plane without thinking about eigenvalues and eigenvectors at all. We could use null lines, for example. 5x minus 10y equals 0 would be the x null line. That's equivalent to y equals 1/2x. 4x minus 7y equals 0 would be the y null line. That's equivalent to y equals 4 sevenths x. These null lines have slopes that are not too far apart. The lines are kind of close together, which does make the phase plane a little trickier to draw by hand if you were trying to draw it by hand. Won't have any straight line solutions though, because we've got complex eigenvalues. Let's now again think about this in terms of change of coordinates. Y equals PU, remember that? PU. That's the way to remember that we get the old coordinates in terms of the new coordinates when we left multiply the new coordinates by P. If you wanted the new coordinates in terms of the old, you got to use P inverse. Gives you this. If you write the du/dt equation using the fact that C in this case equals P inverse AP, that equals C in the end. U is P inverse times Y. So differentiating both sides of that, du dt will be P inverse times dy dt. But dy dt equals A times Y. But Y equals P times U. But P inverse AP equals CU. Or P inverse AP equals C. And P inverse AP equals this. It can be shown that the matrix exponential of this matrix is this. That's not a real easy thing to do, but it can be shown. So that's going to lead us to the unique solution of a generic initial value problem by using the fact, once again, that well, C is P inverse AP, therefore A is PC P inverse. And ultimately, I'm skipping a step here to go from here to here. I've shown it before. E to the TA, the matrix exponential of TA, is P e to the TD P inverse. Here again is P. There's the matrix exponential e to the TD. Here's P inverse. Here's the arbitrary generic initial condition vector. If you take the time to multiply this out, you get this. So it once again helped us solve our IVP, our generic IVP for this system, though I did need technology, at least at the moment, to derive this equation right there. It's not quite the last slide, it's a picture, and then we'll look at Mathematica. We can think of this in terms of skew coordinates, like I've emphasized recently. Here is the phase plane for this system. The x null line was y equals 1/2 x. That's actually the brown one. It's got a slope of 1/2. Solutions cross it with vertical tangents going up over here and down over there. The pink one, that's the y null line. Solutions cross that horizontally, going to the left up here and to the right down here. Brown is the x null line, pink is the y null line. They're very close together, so solutions have to turn in a tight manner, you might say, as you cross here and then cross there again. You got to turn very rapidly. The orange lines represent the u and v axes for the coordinate transformation P, where P again was at first column 5, 3, and second column 0, 1. P maps 1, 0 to 5, 3, and it maps 0, 1 to itself. And what that ends up meaning then is the u-axis of the new coordinate system is parallel to the vector 5, 3, which would have a slope of 3/5. Slope of the brown is 1/2, 0.5. Slope of the pink is 4/7. Well, what is that as a decimal? Somewhere between 0.5 and 0.6. 0.57 or 0.58 maybe? I'm forgetting. The orange one has slope 3/5, 0.6. They're all really close together. But those are the skewed axes, and we could also make the skewed graph paper based on this. So the u-axis is this way. The v-axis is, again, the same as the y-axis. Notice this, from this point to right there would be the vector 5, 3, components 5, 3. And going from here up to there, this line in the graph paper, that's the vector 0, 1. Let's animate this. We could also have Mathematica do the complex diagonalization. The eigensystem A of A is this. If I make P to be that complex matrix, I1, negative I1, you've got to use a capital I in Mathematica, then the inverse can be found. This is what we got. We can compute A times P and ultimately compute, well, okay, I can do the inverse of P times A times P and get a diagonal matrix. Again, that's interesting to round out the theory, though we're not going to use it. Now on to the current example. Here's our A matrix. Its eigenvalues are -1 plus or minus 2i. They've got to be complex conjugates when A itself has real number entries. If we allow A to have complex number entries, then the eigenvalues, if they're complex, don't have to be complex conjugates. Here's our P matrix and its inverse. C is going to be the P inverse times A times P, and it does equal that other matrix. We can compute the matrix exponential of that. We can then compute e to the TA by doing P times e to the t C in this case, and that makes me realize I had a typo in my PowerPoint. In the PowerPoint I had e to the td. I should have made it a C. I'll point it out as the last thing we do. Here's a static phase plane, like I just showed you. Here's a phase plane with the grid in there. And let's now animate this in two ways. I have emphasized recently that there's two ways to visualize this. One way to visualize it is to imagine the axes themselves changing, the x-axis becoming the u-axis, though the v-axis is the same as the y-axis, so it doesn't change. This number a here that's varying from 0 to 1 doesn't mean anything. It's just my animation parameter. It's not related to a number in the matrix. I said you could visualize it that way, though I've also emphasized that that is actually a confusing way to visualize it, because you need to think more carefully about the actual coordinates of the vectors to these different coordinate systems. Another way to visualize it is like this. I did this in the last lecture, 27C it was, but it may have been confusing. It'd be good to go over it again here. It's actually to think about these two linear systems in two different planes. Pretend you've got the plane of the board, maybe that's what this one is in, and a plane just in front of the board, that's what this one is in. And to imagine sets like this disk getting mapped to corresponding sets over here. Under this matrix transformation defined by P. This is your C matrix. Your A matrix, I've already forgotten, is like a 10, -5, 7, -4, I think. Check that out. Hang with me here, I'm going to show you something kind of cool, so hang with me. Where is it? 5, -10. The other way around, I keep doing that kind of thing. 5, -10. 4, -7. This picture on the right is the phase plane we already looked at. This picture on the left is the phase plane for the du dt equation, where du dt is c times u. Much more ordinary looking spiral, you might say, spiral sink. This one here is more of a slanted and elongated spiral sink. It's not even clear, perhaps, that it's a spiral sink, though it has to be because the eigenvalues have negative real part. If you you try to follow this solution curve, for example, you do end up going closer to the origin there. What this visualizes here as the angle changes is the following. For any fixed angle, what I'm imagining here is the sector that's been taken out of this disk here gets mapped to what's getting filled in here. And the fact that the u-axis where you started, this side of this thing that's rotating here, this line segment, on the u-axis, and you're starting it out on the slanted u-axis in the xy plane, means that this positive axis in this UV plane is getting mapped to this line, this ray outwards from the origin in the xy plane. As I continue letting theta increase, I'm going to let it increase to 90 degrees here. I'm going to go to the v-axis. Watch what happens to the graph on the right. If I'm exactly on the v-axis on the graph on the left, it's hard to get there exactly. I guess I could just do pi over 2 here maybe. Pi over 2. Now I'm exactly on the v-axis here. I'm exactly on the v-axis there too. This 1/4 disk that has been taken out of this picture and mapped over to this thing is 1/4 evidently of maybe an ellipse. Actually, not necessarily 1/4, but it's gone to that v-axis, to that y-axis, which is the same as the v-axis in the slanted coordinates, once this line has gone to the v-axis in this rectangular coordinate system. Continue letting theta increase. Let it increase up to, say, pi. Now the half disk that's disappeared over on the left has been mapped to this half ellipse. And so what we're really seeing is not only are the axes getting mapped, so to speak, but also the solution curves are getting mapped. It's like the solution curves that were in the original disk get mapped to corresponding solutions in this ellipse. That's not an accident, actually. It really is what's happening here. And that is not only a cool thing, but it can be a useful thing in ways I'll show you here in future lecture Bs. Thanks for watching.